Hello, everybody. Welcome to the trends and advantages of PHI inverter testing in the development processes of the e-mobility solution. So basically, today we'll talk about PHI application for inverter testing in the automotive and aerospace industry mainly. Today, you have your presenter as myself, as Mathieu Hainaut. So I'm the customer solution architects and partners of a company called DNV, which is a third-party customers at OPAL-RT. I'm actually working at OPAL-RT for the last 10 years, mainly on the integration process and are more like business relation and sales. And I have with me today Abhishek Pandey, actually a field application engineers toward the PHI application and inverter testing. Abhishek will actually be part of the demo and answering your question with me at the end of the webinar. So today, the outline of the presentation is actually the introduction of the concept of PHIL. We'll talk mainly about what kind of solution OPAL-RT can bring to you. And we will run like a demo of the PHI inverter. So actually we had like an actual setup of the amplifiers with the OPAL-RT systems that emulating the machine and the real inverters on the loops. And then we will move forward to a question periods. So first of all, the conventional approach, So the conventional approach that we have to test an inverter is actually to have like a real dyno. So in this concept, like we had the dyno setup with the dynamometers as a load, and we had the real test machine, in your case, probably a PMSM or induction machine with the right drive system and controllers. The challenge with that is you have a lot of mechanical component for doing the dyno. The dyno is actually a really expensive cost to operate as well. It's have mechanical movement, so it's prone to break in some cases, and it have limited capability to actually execute some fault in the systems. And also the turnover to change different setup might be really long and not cost efficient. So a main application we saw is like to pass from one application to the other might take hours and days for building the setup, actually turnover, changing the motors on the bench will require any calibration, new brackets. It's a long process. So to help our engineers, we're looking towards to bring the PHIL concept. So instead of going to a full dyno and have a real machine models on the loops, we're looking to test the controllers and its inverters directly to a more flexible approach, which is motor emulators, where we use amplifiers and the machine that we use at the OPAL-RT to emulate the machine behaviors, actually the back EMF. So that actually like allow you to do a lot of testing way more faster. For just an example, like changing from one topology to the others is just connecting the three-phase machine inverters, and actually we can change the topology of the machine on the fly. An application we had like with the customers is like they want to test a broader scope of different impedance of motors for a single drive. So with the emulators, as an example, we can actually swipe the impedance of the motors virtually and have like this the same behaviors of a real machine without having any mechanical or physical changes to the systems. So to achieve this kind of application, like we partnership with a company called Inverter based in the US, actually that bring the power stage. If you look at their systems, they provide two solutions. We have on the right the EME, the E-motors emulators. This is the back EMF amplifier for a three-phase or six-phase machine. And we have the DCE, which is the DC bus. So the DC bus, it could be used to actually provide a DC to the inverters and also power up the whole bench as the EME. So if we look at the general concept there, so we have a single bench called the EME where you connect the traction inverters on the left. So the main concept of the EME at DNV is to save you power by recirculating the power in the same cabinet. So we create a DC bus inside the cabinet where it's shared between the DC power provided to the inverters and as well it's power up the back EMF emulators for the 3-phase or 6-phase application. So any power that actually been consumed by the DC power to be pushed as a phase motor control to the back EMF emulated by this machine will be actually like recirculated to the internal DC bus of the cabinet. Which that means is at the worst case scenario, the bench will only consume 25% of the maximum rating of the test capability of this bench. So that actually like allow you to have less losses in the system, and actually you don't need the physical high power connection in your system. Actually, you can lower the specs in your lab's capabilities. Also, all racks from DNV are on casters, so it's allow you to move it around. We'll see that could be an advantage because a more bigger system could actually be decoupled and actually used as two separate entities and be connected together at the end for a bigger power capabilities. It's like the footprint is really smaller compared, like if you compare that to a dyno, like we're talking here to a standardized cabinet size at actually a 2-meter height for your labs. And actually, like with the combination of OPAL-RT machine, which is like actually come from the RTS systems with our PMSM or induction machine, we can emulate all kinds of different machine behaviors up to the special harmonics of our machine. If we're looking at the power rating now, so if we're looking at the single cabinet, single channels, because it is really important to know that all of those cabinets have two the main configuration is like single channels, like 3-phase single channels, or 2x 3-phase. Actually, that will double down the power. So a main unit of a 3-phase output for the motor mission go up to 275 kilowatts. The DC voltage to the traction inverters is 960 volts. So that gives you actually DC current of up to 300 amps and with a peak of 430. And on the each AC phase is 350 amps with a peak of 550. This is like for the main single channel cabinet. And in this case, we can actually embed the DC supply for the whole system in the same cabinet. Now, if you want more power density, we can have the EME in the center here with a dual channel configuration. So what happens is like all the power rating and the current are double downs. In this case, we can actually use it as a single 3-phase output with double down the powers. Or you can actually use that as two separate machines of 3-phase, or we can actually have a single 6-phase machine with those AC current and power ratings. Because of that, since we're now using a 2-channel configuration in the single cabinet, we need to get out the DC emulators out of the bench because there's no more space in the cabinet. So with those power, you can expect to have a 2-cabinet solution. Again, OPAL-RT bring his machine models to the whole system and actually control the whole setup. And if you want either more powers, you can actually double down the whole concept and actually go to a 2-cabinet for the EME. In this case, we again double down the dual channel. So we're now like at a 4-channel configuration in total. So if you have like traction inverters that really need like those high current, peak current, like we're now talking about the 1400 on the DC phase current up to 2200 peak amps per phase. And we're talking here at the 1.1 kilowatt total powers that can be used in this bench. Keep in mind that this is the power, this is the nominal powers. So since we're recirculating the whole powers, we just need 25% of this powers in the lab available to power up the whole systems. When you have like higher power capability with like multiple channels in the EME, you have the chance here to actually like decouple the system and use it as a big single system as conversion D or C. So basically I have all the 4 emulators connected in parallel to have like higher power for a 3-phase or 6-phase application. Or you can actually separate the EME to have lower power, but like more motors capability. So basically I have 4 motors or 2 motors configurations. So actually, this is allow you to, if you have a car with 2 motor configuration, if you have like the whole capability of the bench, you can actually have 2 3-phase motors for the dual motor configuration. And let's say if you have like a higher motor power range in your car, you can actually like combine them together to have like the higher power. So there's a lot of flexibility to that. And that's actually returning to the caster on the system. So actually, we have customers that have 2, 3 different labs, and they move around the emulators quite easily from one lab to the other, depending on the configuration they want. So they have the high power labs and the lower configuration lab as well in the building. So after that, like this is the DNV part. So we're moving up to the OPAL-RT part. So actually what OPAL-RT model specialty in real time bring to the DNV partnerships. So our standard configuration is based on RIP of the machine models, like either PMSM or induction machine that we'll see later, running on the NI PXI systems under the Veristand software. So Veristand software is a really flexible tool to enable real-time applications. So it gives you a customization of the platform. So you can actually adapt that to yourself, create HMI. As we will see in the demo, like the HMI there is the Veristand HMI. So you can have like a graphical control interface. Actually, you can change that on the fly during the real-time simulation. So if you miss an information, I see our developers and they see like a check to having stuff to be seen on the behavior of the machine. You can actually test automation. So you have script or they actually have their own NI tools to actually automate scripts. So if you want something that run, create reports, that's perfectly doable. We support a lot of model integration. So yes, we bring at OPAL-RT the machine models for the electrical behavior. This is our specialties. But if you want to implement third-party software, like Basuning is one of them, the most common. But like I've seen people integrated CarSim, for example, for the vehicle dynamics. So the vehicle dynamics, depending on the torque of the motors and the situation, actually is provided by the third-party modeling in the same environment, running in Veristand / NI as CarSim. That's an example. And actually, like that's actually like can reduce the development time as well. Veristand is an open platform that we encourage our customers to actually get used to it and adapt and be autonomous on the system, so they can actually like change everything by themselves if needed, so that you don't rely on it of any like third-party services if needed. For sure, we have our specialty. So if you prefer to have like our assistants, we're always happy to help on those projects. If you look at the technical architecture of the Veristand and the hardware of PXI, so technically you have the host piece interface, which is a PC where you will run the Veristand softwares. It will be connected through Ethernet to the real-time system as the NI-PXI. This is like a modular, we'll see that. So a backplane with multiple cards in there. And you have like FPGA, which is where we run our machine models. But you can actually have different cards for like a communication, that is CAN, LIN, FlexRay. You have like more general output as well. NI and OPAL-RT actually have been developed like an SLSC board. The SLSC is really a conditioning unit. So any IOs or communication can pass through the SLSC and be adapted. So what we bring here usually is like fault injection capability. You have resolvers, but you have your sign and cost. We pass the sign and cost signals through the SLSC cabinet, chassis actually. And you can actually apply real fault, like open signals, like losing one signal is what happening. to the device under test that you're testing. We can actually conditioning signals. If we return to the resolver, because this is the main signal that's been passing through the SLSC, we can actually adapt the voltage to your needs. Typically, the output of the PXI is 10-volt signals, analogs. The SLAC have the capability to increase this voltage to your needs, like 20, 40 volt, peak to peak if needed. Also, we have an additional buffer here to push more current to avoid the resonance on the cabling. So the SLAC is really like a passive conditioning boxes. So if we look again at those, the PXI, there's many modules, so we adapt it to your needs. So, but on the lower solution for the DNV application and inverter testings, we actually bring the FPGA with SFP communication to the DNV equipment and a CAN cards for general controlling of the bench. And the CAN could be also used to control the DUT as a minimum asset. We also bring the SLSC for conditioning the resolver signals mainly to actually gain more current on the analog to avoid resonance on the systems. And we mainly see resolver signals above 10 volts. So like the SLSC is there to have that. But if you have any additional needs, like thermal sensor that you want to emulate, both the PXI and the SLSC, depending on which load that you have, could be adapted to your needs to different sensors. So like really for there, like depending on what your needs, like if you want to do stimulate more channels to your device under test as the inverters and the controllers, that could be added to the system that you have here. If you look at more like at the connection diagrams, like what we have here, again, we have the Windows interface with this Veristance, but the minimum asset that we provide with the DNV is actually 2 FPGA cards, like the PXI 6592, which is an SFP board from NI, where we have the single SFP connection to the EME. Actually, we can control 2 EME full benches. So remember the 2 benches EME cabinet that we see previously. And we can actually control the 2 DC with this board. So this is where we put our PMSM models or our industrial machine, like all our OPAL-RT IP is from the modeling that will lie on this FPGA. We have a second FPGA as well for other resolver behaviors. So like we send the angle to the second FPGA and we generate the resolver behaviors there. So from there, we have customers that actually build custom tables for the resolver pattern, actually to emulate fault. So like it's a really flexible platform where if you want to have the resolver signals here and play with it, adding harmonics, behavior, unbalanced sequence, we have the capability in the system, especially with this FPGA, to generate all those signals as well. We also have like a voltage feedbacks for the model loops coming from this card. So actually, like we take the 3-phase voltage from your inverters to detect the controlled commands from that, and this is what is injected to our machine models on the systems. So Veristance, this is like the base software that you will mainly use to control the whole bench. So what we do is we, with the partner, we create like we call that the custom devices. The custom devices is a project's part to actually control the DNV. So from there, you have the firmware, you have the machine models, you have the IO channels. So like with the custom models, you're ready to go to take the OPAL-RT machine and control the DNV. So from there, as a project in Veristance, you can actually add a lot of stuff. So you can actually add your test automation as we talked before. You can actually add your third-party machine models in MATLAB or MapleSoft, GT Suite, or CarSims in certain configuration. You can create your HMI. You can manage your IO. So if you have any like thermal models of the application that could be used, for example, in MATLAB Simulink, and controlled by Veristance to control IO channels. It could be in this case of thermal, a variable resistant card that you can add to the PXI chassis. So it's a really flexible that we actually can grow with you. If we look at the machine models, like our offer at OPAL-RT, the most common we see the PMSM machine models that we have. That could be like a PMSM or a BLDC. We have actually three variants of these models. We have the simplest models and the DQ models. We have the fixed DQ. So really to start up the application without any worry, like it's a really simple model to start with. Then you can have the variable DQ model, so a little bit more complex. That actually allow you to import the 2D tables from either a table that you have or from common software at GMAG, Maxwell, or model solvers to actually have a better accuracy on the back EMF small harmonics. And then if you want to push the model fidelity further, we have the spatial harmonics. So we really work with GMAG Maxwell to have a 3D table import directly on our solvers on FPGA to be pushed. So from there, you have the full harmonics and current harmonics behaviors of the machine that you develop. So if you look a little our partner with that, we have the NSYS Maxwell technology and GMAG are the two most common that we see. Actually, we take those 3D flux models and we import them to solvers. If you use any other software, like I encourage you to contact us. We actually have script that change those type of flux tables and we adapt it to our solvers. So probably we can adapt our script to your source of data. Then after that, like we have like a small difference, like the classic DQ versus the Philip FE models. So you can really see that if you push the flux model, depending, you can really see a better curve representation of the machine models and the systems. In the same idea, we have the induction machine, so we can actually simulate squirrel cage machine, doubly fed injection machine, and generators. And there we have the DQ and the VDQ algorithms. So again, we can import 2D table from GMAG and Maxwell. So we know that in the e-mobility, we actually have more and more induction machine demands. So it's something that can be run on the OPAL-RT and the NV application for testing your inverters. So in conclusion, like the OPAL-RT and DNV partnership is really to increase the flexibility and your test agility in your systems. OPAL-RT are specialists of HIL, and we actually couple with DNV, we can go to the PHL application. So we can really follow you up from the R&D development of the controllers. Keep in mind that OPAL-RT have all the tools as well in this same platform of DNI chassis to test the controller without the inverters. So we can actually simulate the inverters as well in the system in a pure HIL way. So when you have the HIL setup, this could be moved forward to the PHL. So we remove the virtual inverters and we had the real inverters and we had the DNV power EME to test the real application on the real powers with that. So we can actually do drive cycle, torque ripple management. So we can create fault on the system, like shorting to phase to see how the inverter react and protect itself. Then after that, like keep in mind that those tests are really good as well for testing the thermal endurance of the inverter. So you can actually like having our models with the DNV and run that for like a week period if you want at full power. So it's really a nice way to do that. And since you don't have any mechanical behaviors as a dyno, it's really more cost efficient to run those endurance testing at full powers. So we can really like help you towards your V cycles from the R&D to the production phase of your test. Now we're heading to the demo with me and Abhishek. So actually, we've been to the DNV facility in Auburn Hill, Detroit, Michigan. So actually, they have like a real component there with our machine, and they're ready to invite you if you want to see a real application. You can bring your inverters if needed. This is a testing facility that they have in the Detroit region. and they're really open to see you and present you our solution. So let's go to see the demo.
Welcome to the live demo of PHL inverter testing with OPAL-RT and DNV. I'm Mathieu Hainaut, the account manager for the partnership with DNV. I'm currently at the Auburn Hill facility of DNV, where they actually test their equipment and actually using OPAL-RT technology to test inverters. And I would like to present you the demo with the equipment. In this demo, the presentation will be in 3 sections. First, we'll introduce you to the hardware that we're using today for the validation testing. We'll show you the OPAL-RT IP and what OPAL-RT bring to the DNV equipment for testing inverters. And we will go to a live demo using the software and doing a closed loop environment with the inverter that we have in the lab here. So let's start it. So at first, we have the DNV equipment called the EME. It's a full cabinet for power management and connection to the inverters. So this cabinet is a 2-channel cabinet. It can control 2 different inverters of 3-phase, or it could be connected for a 6-phase operation inverters. The power density that you have here is, each channel is 3-phase of 275 kilowatts, up to 350 amps RMS per channel. So if you purchase the combination of 2 channels, you can have a power density in this cabinet up to 550 kilowatts, 700 amps RMS in this cabinet. What you have here, you have the control for the whole bench that the DNV provide. You have probe here for measuring your voltage or current coming from the equipment. To a scope, you have all the encoder, resolver, low-level signals for connecting your inverters, and we have the connection to OPAL-RT systems. Now let's go to the back to see the connection to the inverters. So we're now in the back of the EME cabinet of DNV. So first of all, like here at the back, we have the SFP connection that we will use for OPAL-RT connection real-time systems. And here you have the 2 channels as channel A and channel B. So you have your DC connection and you have the 3-phase connection to the inverters. As you may see, like there's 2 channels, so 6-phase in total. It's up to the customers to use it as 2 independent systems or a 6-phase machine as well as interconnections. Keep in mind that we have the line inductance in this equipment as well. We offer at first the 105 microhenry or 210 microhenry options. If something differs for your application, that could be changed as well for the applications. Now let's go to the inverters. So now we are in front of the inverter cabinet. So if we open that, we have here a Summicron generic inverters for a 3-phase PMSM machine. This will be the inverter that we'll use as today during the demo. Now we're moving to the accessory cabinet. This is where we provide to the a lot of equipment for the customers. So we have scopes, we can actually have like power measurement units, and we have the real-time system that OPAL-RT provide as a PXI chassis with our NI partnerships. From here, the main important component is really to have the controllers for the real-time application, and we provide like the FPGA for the SFP communication. The SFP is where the single first link that we need to connect to the DNV equipment. So OPAL-RT FPGA model of machine, either like a PMSM induction machine, is controlled by the fiber optics back and forth. So we receive all the measurement, we close the loop with the amplifiers of DNV to the inverters. And then we have also like a lot of low-level signals. We can use them for temperature sensors, but especially we measure the voltage to close the loops to the inverters. And we can generate as well resolver signals. So in this case, like both DNV and OPAL-RT have the encoded machine. We're both capable of simulating the resolvers or encoder signals, but OPAL-RT bring you more flexibility on the resolver signals to create fault, disturbance, adding noise to your resolver signals if needed. During the live demo, we'll see like how the machine operates with the OPAL-RT systems. Now let's move on to the last equipment that we have during the show. So now we're in front of the equipment called the DC application. This is the DC supply that the DNV equipment is using. So this is the fast transient DC supply. This is one option to provide a DC to both the amplifier cabinet and the inverter as well. This is like a special equipment that DNV can provide. It's a DC source yet, but as well, it's up to a 20 kilohertz bandwidth DC supply. So it can not just generate a DC source, but it can actually generate like a 2 Cradon 20 kilohertz signals. So you can use that to actually add noise. So OPAL-RT also bring the fast connection with the real-time systems to this equipment. So if in your test sequence you want to do any perturbation on your DC, OPAL-RT with the NI platform can do those modeling and adding noise and fault to the DC with such equipment. So this is like the full overview of the application that we have as hardware. So now like I will pass to the software and closed loop operation of the software with my colleagues called Abhishek. He's a field application engineer and colleague of mine. Thank you.
Hey everyone, welcome back. Now we're going to take a look at NI Veristand, which is the software solution provided by National Instruments for real-time applications. We have a project here called Gen 3.1 Demo. Under the project, we have multiple custom devices. We have the DCE, the EME, and the Power Electronics add-on. The PE add-on is an add-on developed by OPAL-RT for solving electrical circuits and motor models on the FPGA. Let's move our attention to the front panel screen. The DCE is in the enable voltage command mode, and I will enable or demand a voltage of 300 volts. The EME state command is the enable PM mode. I will start the DUT, put it in torque control mode, and enable the PWM. Now I will demand a speed of 1000 RPM. We start to see some waveforms from the resolver. These waveforms are coming directly from the EME. I will also demand a torque of 5%. And we start to see three-phase IABC waveforms come in on the scope. Let's try to increase the speed to 2000 RPM and the torque to 10%. One of the capabilities that we have with this solution architecture is to actually do 4-quadrant operation. So right now we're motoring. I'm going to demand a negative torque, and we see the IQ shift direction, and we also saw a phase reversal in the 3-phase IABC currents. We can also demand a negative speed, and a negative speed with a positive torque. The second test procedure that we will run is stall torque. So I will reduce the torque to 5% and take our speed down to 0. As you can see, we're still generating torque and the DUT is still reading a torque. The third procedure that we will run is inserting a drive cycle and controlling it through the sequence control panel right here. We will first raise our voltage to 350 volts. And I have a preloaded drive cycle, which I will run right now. You will see how our drive cycle commands different torque and different speed, and our waveforms, they comply with the requirements right here. We just saw a demonstration of motor emulation and motor control. Because of the high power components like the EME and the DC involved here, this sort of HIL simulation is called PHIL, or Power Hardware in the Loop. What OPAL-RT adds to this product is higher fidelity motor models, resolver fault injections, and DC noise injection. These will be a part of a future demonstration. Thank you, everybody.